Is going to show you how you can run a paired sample t-test in SPSS. I'm going to work problem 10.40 from Siegel, which I like to call the lie detector problem. Here's the problem. Stress levels were recorded during a true answer and a false answer given by each of 6 people in a study of lie detecting equipment, based on the idea that the stress involved in telling a lie can be measured. So test whether the stress levels are different. The way to think about this is that we've recruited 6 subjects, we've put the equipment on them, we've asked each subject to make a true statement, we measure their stress level. Then we ask the same person to make a false statement and measure their stress level. And we'd like to understand whether the stress levels when telling a lie are higher than those when telling the truth. This is a paired sample t-test for the following reason. Recall that paired sample t-tests are used whenever you have 2 measurements on each subject, and that's exactly what we have here. So whenever you have a before-after situation where maybe I measure your weight before putting you on a diet, I put you on the diet, then I measure it afterwards. So that's a before-after situation. Or in this case, we have 2 measurements when telling the truth or telling a lie on the same subject. So when you use an independent sample t-test when you have 1 measurement on each of 2 different groups. Okay, so if I have a treatment group and I measure them, and I have a control group and I measure them, okay, I have 1 measurement on each group. Okay, so the point is we have 2 measurements on each subject, therefore we use a paired sample t-test. All right, the way we do a paired sample t-test is that we focus on the difference between them for each subject. So let mu be a parameter that we want to estimate with this sample. Mu is going to be the true mean difference between false and true. So if I take, in this case I took false minus true, so 13.1 minus 12.8 is 0.3. That is the difference for subject 1. 1.1 is the difference in stress level for subject 2, and so forth. Looks like subject 4 actually experienced more stress telling the truth than telling a lie. Alright, so if the lie detector has absolutely no effect, then the mean should be 0, right? There should not be any difference in stress levels between telling the lie or telling the truth. So that's going to be my null hypothesis. Now, I'm going to use a 2-sided alternative since coming into this I have no prior belief as to whether stress levels would be higher or lower. So we'll just be conservative and use a 2-sided alternative. All right, we worked through this in class. We found the standard error and we found the p-value. Let's now do this in SPSS. So in SPSS, we're going to put the numbers side by side. The general rule in SPSS is 1 row per sampling unit and 1 column per measurement. And so therefore we have true and false as separate columns, and these are as the rows. So to do an independent sample t-test, we're going to go up to Analyze, Compare Means, and then Paired Sample t-test. The menu is very easy to use. We'll just copy one variable in one column, the other variable in the other column, and that's about it. We can go look at options for a second. We're going to get a confidence interval. If you want something other than 95%, this is where you would change it. There's really nothing to do here at this point since we're quite happy with 95% confidence. Go hit OK. Now, why don't we go back to the course packet for a second, and I'm going to try to make this a little bit smaller so that I can show you a comparison between what's in here and what's in the course packet. So first off, the mean response for true is 8.5, the mean response stress level for false is 9.2. These both show up in the descriptive statistics box at the top. Now, if we find the difference, the mean difference was 0.7. It looks like SPSS decided to take true minus false, whereas I took false minus true. That's okay. They found the mean then as minus 0.7, where we found it to be 0.7. The standard deviation of those differences was 0.648, and that's exactly what SPSS finds here. Now, how did we find the standard error? Well, remember the standard error is going to be the standard deviation over the square root of n. So it's 0.2646. That describes how variable is this random variable x bar, the sample mean. And you'll see that that shows up in this SPSS box. Now, SPSS gives you a confidence interval. I didn't compute that on this page. This is going to recall that we can use the confidence interval approach. If this contains the reference value, then you can't reject the null. In this case, the reference value is 0. The confidence interval does not contain 0, so we reject it. If we wanted to do a t-test, though, with p-value, I did that on the page here, so it's 0.7 minus 0 over the standard error. The t statistic is 2.66. Notice that we get exactly the same thing in SPSS. Actually, it looks like the numbers vary slightly. I better double check that. We can find the p-value, as I did on the slide, to be 0.0457, which is exactly what SPSS gets. And here's our conclusion. All right, so that's how we would do this in SPSS. I actually don't like the menu in SPSS because it leads you to jump right to these statistics without looking at your data first, and I think it's really important to look at your data and make sure that the assumptions of this test are satisfied. So what assumptions must be satisfied? Well, the distribution had better be normal, especially given the small sample size. So if we wanted to check that, remember what has to be normal is the differences. So let's go compute those differences. I'll go up to transform compute, and I'm going to make a new variable called diff. Now I'll take true minus false, I guess, to be consistent. It really doesn't matter. It's just going to change the sign. So now we have a new variable called diff. And these values are assumed to be normal, or they better be normal if we're going to use this test. If they're not normal, then we're not allowed to use the test. The best way to evaluate normality is to go to Descriptives Explore, and we'll copy diff in. Then let's go to plots. So let's get a histogram. I like my histograms. We don't need a stem and leaf. I'll turn that off. And then let's go check off normality plots with tests. And that's all there is to it. Go hit OK. And it takes SPSS an amazingly long amount of time to analyze 6 cases. Okay, here we go. We're back. So the first thing we should really do is look at our data. The histogram doesn't show any outliers. We only have 6 cases, so the histogram's not all that interesting. I'd get very worried if I had some outliers. What's more interesting is to look at the QQ plot. The points have approximately fallen on a line indicating that normality is not really in question. If we wanted to do some formal tests, we can go look here at the tests of normality. The null hypothesis for these tests is that the data come from a normal distribution. The alternative is that it's not normal. Let's start with Shapiro-Wilk. The significance level is 0.4, indicating I cannot reject the null hypothesis of normality. Therefore, it's entirely plausible that I've sampled from normality. I can therefore go ahead with that test that I did earlier. Kolmogorov-Smirnov gives us the same conclusion. Can't reject the null hypothesis of normality. One other thing that's kind of useful to note is we really didn't even need that paired sample t-test. We could have just done everything from Explore. Notice that we get exactly the same confidence interval for the mean, so minus 0.0199 minus 1.388 is what we got before. That does not contain the reference value, leading us to reject the null hypothesis that the means are different. Therefore, we conclude that the stress test works. So that's how we do an independent sample t-test in